Welcome everyone. Today I am going to discuss about sets. A set is defined as a collection of objects which are grouped according to a well-defined description. Each object is called an element or members of a set and is represented by the Greek letter epsilon. A set is denoted by a capital letter, and all members of the set are placed inside a pair of braces and separated by commas. Let us have this example. A is a set of books, notebooks, ball pens, and pencils. B is a set of apples, bananas, oranges, melon, and grapes. C is a set of paracetamol, antibiotics, vitamins, and you will see this three dot symbol. We call this one as ellipsis, and we read this as etc. or and others. That means there are still other objects belonging to set C having the same description as that of paracetamol, antibiotics, and vitamins. Then we have another set D, and we read this one as D is a set of X such that X is a biscuit. That means all biscuits belongs to set D. So looking at the given sets, so we can say that books is an element in set A. And this is represented by the symbol books. Then you have there the epsilon for element and then A. We read this one as books is an element in A or books belongs to set A. Oranges is not an element in set C. So we go back to set C, you will notice that you have in there the elements paracetamol, antibiotics, vitamins, and other medicines. So since oranges is not an element in set C, so this statement is true, and we write this one in symbol as oranges is not an element in set C. Take note of the symbol for not an element. So you have in there the symbol for element with a slash. So we read it as not an element, or oranges does not belong to set C. So we have skyflakes is an element in set D. So notice in here, D is a set of X such that X is a biscuit. And since skyflakes is a biscuit, then we say it is an element in set D. And write that one in symbol as skyflakes is an element in set D, or skyflakes belongs to set D. There are two methods of writing a set. The first method is the roster method, which is also known as the list method. As the name itself implies, in the list method, all the objects are listed in the set. Examples, we have A is the set of books, notebooks, ball pens, and pencils. That means all other objects which are not found in the list does not belong to set A. So we have set B in here is the set of apples, bananas, oranges, melon, and grapes. So that means any other fruits or objects which is not found in the list does not belong to set B. The second method is the set builder notation, also known as the rule method. So in this notation, the set indicates a well-defined description of the elements. For example, D is the set of X such that X is a biscuit. So this one tells us that all biscuits belongs to set D. And objects which is not a biscuit does not belong to set D. Let us have this example. Write the set of letters A, E, I, O, U in two methods. So in the first method, the roster method, what we're going to do is simply write all the elements A, E, I, O, U inside the braces to indicate a set. So we can denote that one with any letter, capital letter in the alphabet. So in here, we let C represent the set containing the elements A, E, I, O, U. And in the set builder notation, knowing that A, E, I, O, U are all vowels, we can say C is the set of X such that X is a vowel. Let us now discuss the set of real numbers. The set of real numbers can be represented by this double-arrowed straight line, which we call the real number line. So all real numbers can be arbitrarily located in the real number line. Now, when we were still young, we learned mathematics by first learning how to count 1 to 10. So we started counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And as we grow older, we learned that we can actually count beyond 10. So we started learning how to count 11, 12, 13. So we learned how to count up to 50, up to 100. And we learned that there are still other numbers following after, or counting numbers following after 100, as indicated by this arrow. So all of these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on going to the right, are what we call the counting numbers or the natural numbers. Okay, so we now have our set of counting numbers. N is the set containing the numbers 1, 2, 3, 4, and all the other counting numbers after 4. In the rule method, we write n as the set of x such that x is a counting number, or n is the set of x such that x is a natural number. It is important to note that in the set of counting numbers, 1.5, 2.5, or 3.5 is not included in the set. Okay, so no decimal number is included in the set because they're not included when we count. Okay, so after learning how to count, we learned that there is also this number 0. Okay, so the set of whole numbers is the set containing 0 in the set of counting numbers. So the set of whole numbers includes 0, 1, 2, 3, 4, and so on and so forth. So as we learned in higher mathematics, we learned that these counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or the natural numbers, since they are located to the right from 0, are also called as positive integers. Our positive integers, take note, are also known as counting numbers or the natural numbers. That means 1.5 is not a positive integer, or 2.5 is not an integer. Okay? So each counting number has a negatively signed numbers equidistant and directed to the left from 0. And these numbers are called negative integers. So we have our negative integers. If each of these 1, 2, 3, 4, 5 are positive integers, so we have these numbers directed to the left from 0. We have our negative 1, negative 2, negative 3, and so on. Each of these counting number has an equidistant and negatively signed number directed to the left from 0. And they are what we call the negative integers. So take note how we denote our set of negative integers. So our set of negative integers includes numbers coming from the left. Then we have negative 3, negative 2, negative 1. So these three ellipses in here again indicates the negatively signed integers. Okay? So we have the set of integers includes now the set of negative integers, which is this one to negative 1, and then the set of whole numbers. So our set of negative integers are the set of negative integers, 0, and then the positive integers. Okay, so we denote that one in the rule method. Z is the set of x such that x is an integer. Recall again that when we say integer, we are referring to the counting numbers, 0, and the negative of the counting numbers. So take note, negative 1.5 is not an integer. Okay, or 5.5, it is not a positive integer. Okay, so look at the space between integers. So when we have between 1 and 2, there is that distance. Between 2 and 3, there is that distance. Between negative 1 and 0, we have this distance between these two numbers. These two represent numbers. Okay? Okay, so we just learned the set of natural numbers or counting numbers or the positive integers. So we have our n is the set of the numbers 1, 2, 3, 4, and all the other counting numbers. Then we have the 0 and the set containing 0 and the counting numbers is what we call the set of whole numbers. Then we learned about the negative of our counting numbers. Negative because they are directed to the left from 0. So we call them the negative integers. So the negative integers and the whole numbers makes up the set of integers. We use z to denote the integers. This is actually from the German word Zahlen, which means number. Okay, so let us take a closer look on the numbers between integers. So we have in here 1, 2, 3, 4, and the space between these integers also represent real numbers. And we call these numbers as decimals. There are three types of decimals. We have the terminating decimal. Example, we have 2.5. So we know 2.5 is between 2 and 3. So this is our 2.5. Or we have a decimal 2.9. So we know 2.9 is greater than 2.5 but less than 3. So we can approximately locate that one in here. This is 2.9. So these are examples of terminating decimal. Another type of decimal is the non-terminating repeating decimal. Example, we have 1.3333. So the digit 3 is repeated endlessly. So we can approximately locate 1.333 somewhere here. We also have numbers such as 3.666, so we can locate that number somewhere between 3 and 4, so 3.666. Now, these two types of decimals, the terminating decimal and the non-terminating decimal, can be expressed as quotient of two integers. Example, the 2.5 may be expressed as 5 halves. The 2.9 may be expressed as 29 over 10. 1.3333 may be expressed as 4/3, or 3.6666 may be expressed as 11 over 3. So the terminating decimal and non-terminating repeating decimal can be expressed as quotient of two integers. These numbers, which are non-integers, can be expressed as quotient of two integers, and we call them the rational numbers. So a rational number is a number which can be expressed as quotient of two integers. So P and Q in here are elements of Z, meaning they are integers. Okay, the third type of decimal is the non-terminating, non-repeating decimal. For example, we have pi. So pi is a non-terminating, non-repeating decimal. We have square root of 2. So these types of decimals cannot be expressed as quotient of two integers. And we call these numbers as irrational numbers. Okay? So the set of rational numbers and irrational numbers makes up the set of real numbers. So all numbers between integers are decimal numbers, and these decimal numbers can either be terminating decimal or non-terminating decimal, which can be expressed as quotient of two integers, or non-terminating, non-repeating decimals, which we call as irrational numbers. Okay? Let us have more examples on writing sets in roster and set builder notation. The set of numbers 4, 6, 8, and these three dots represent other numbers following the characteristics of 4, 6, and 8 up to 20. In the roster method, we can just write this one as A is the set of numbers 4, 6, 8, and other numbers up to 20. In the set builder notation, we have to take a closer look and have a common description of all the numbers in the set. So the numbers are 4, 6, 8, 10, 12, 14, 16, 18, and 20. We know that all these numbers are even. So we can write this one as A is the set of X such that X is greater than or equal to 4 but less than or equal to 20, and X is even. So take note of this symbol. That means X can have value equal to 4 because 4 is equal to 4 but less than 20. X can also be equal to 6 because 6 is greater than 4 but less than 20. X can be equal to 10 because 10 is greater than 4 but less than 20. X can take a value of 16 because 16 is greater than 4 and less than 20. X can also be equal to 20 because 20 is greater than 4 but equal to 20. And each of those numbers is even. Okay, another description that we can give for numbers 4, 6, 8, 10, 12, 14, 16, 18, and 20 is that they are numbers which are even and they are greater than 2 but less than 22. Okay, we have another example, the set of numbers -5, -4, -3, -2. Then we have the three dots again, telling that we have other numbers which are not written, which follows the same characteristics as that of -5, -4, -3, -2, up to 50. So in the roster method, we can just write this one as, you have set D in here is a set of numbers -5, -4, -3, -2, and so on up to 50. So in writing it in the set builder notation, again, we have to take a look at the properties of these numbers. So you will notice that -5, -4, -3, and so on up to 50, they are all integers. So we can write it as X, or D is the set of X such that we have our X is greater than or equal to -5 but less than or equal to 50, and X is an integer, or X is an element of the set of integers because Z is the set of integers. Or another method, maybe you can describe it as your X, or D is the set of X such that X is greater than -6 but less than 51, and X is an element of the set of integers. So take note in this statement, X cannot be equal to -6, or -6 is excluded in this statement, or X is less than 51, meaning X cannot be equal to 51. So you have your values of X in here will only be equal to -5, -4, and so on up to 50. We have another example, the set of all numbers greater than -5 but less than, or the set of all numbers greater than -2 but less than 5. So if you will look at the real number line, notice that there are a lot of decimal numbers which is greater than -2 but less than 5. So there is no way we can write them all in a set. In the set builder notation, then we can just say you have your set is the set of x such that x is greater than -2 but less than 5. Okay? We have the finite and infinite sets. A set is said to be a finite set if all the elements of the set can be counted. So it may have a very large number of elements, but they can still be counted given enough time. An infinite set is a set where it has infinite number of elements, or the number of elements cannot be counted. Example, we have here A is the set of Y such that Y is a month of the year. So we know that there are only 12 months in a year, so therefore this is a finite set. B is the set of X such that X is greater than or equal to 0 but less than 1 million. So we have, and your X is an element of the set of integers. So since we can count numbers from 0 up to less than 1 million, so we have in here, this set therefore is a finite set. C is a set of numbers 2, 4, 6, 8, and all other numbers following the characteristics of elements 2, 4, 6, 8. Then we have 996, 998, 1000. That means set C in here is the set of all even numbers from 2 to 1000. So since we can count them all, then this is a finite set. D is the set of numbers -6, -3, 0, 3, 6, 9, and so on, and other numbers following the characteristics of these numbers -6, -3, 0, 3, 6, 9. And you will notice after 9 we have 12, 15, and there are still other numbers going to the right which follows the same properties. So there is no end for our set of real numbers. Therefore, we have an infinite set. E is the set of, you have in here the 3 dots telling us that there are other numbers before -10 which follows the same characteristics as -10, -5, 0, 5, 10, 15, and then we again have in here the 3 dots showing us that there are still other numbers following the same properties after 15. Or we're actually talking in here about all real numbers which are divisible by 5. And so since there are infinite real numbers which are divisible by 5, then we say this is an infinite set. Then we have F is the set of X such that X is greater than or equal to 1 but less than or equal to 2. So take note in here, when we have X greater than or equal to 1, less than or equal to 2, we are referring to all numbers between 1 and 2. And we know that there are infinite number of decimal numbers between 1 and 2. And so we say this is an infinite set. The cardinal number of a set is referred to as the number of elements in a finite set. Example, A is a set of Y such that Y is a month of the year. And since we know that there are 12 months in a year, so we say the cardinality of set A is equal to 12. This is the symbol for writing the cardinality of a set. Or we read this one as set A has a cardinality of 12, or the cardinal number of set A is equal to 12. In the second example, B is the set of X such that X is greater than or equal to 1 but less than 100, and X is an element of the set of integers. So this set tells us that included in set B are all counting numbers from 1 to 99 because x is less than 100. So 100 is not included in the set. So we have therefore the cardinality of set B is equal to 99. And another way of writing for the cardinal number of a set, we just put the name of the set inside the vertical bars, and we have this is equal to 99. So the cardinal number of set B is equal to 99. C is the set of numbers 2, 4, 6, 8. You see these three dots again. This one tells us that there are numbers which are not written in the set having the same description as of 2, 4, 6, 8. And then we have 996, 998, then 1000. So set C, therefore, if we look at the numbers written, is the set of all even numbers from 2 to 1000. And if you are going to count all those even numbers from 2 to 1000, you will know that the cardinality of set C is equal to 500. Again, another way of writing is you put C inside the vertical bar. So this is the cardinal number of C is equal to 500. That means there are 500 objects or elements in set C. Equivalent sets. So two sets are equivalent if they have the same cardinality. This symbol, which we can read this one as A is equivalent, or set A is equivalent to set B, will tell us that set A and set D have the same number of elements. Or we have in here a set containing the elements A, B, and C is equivalent to the set containing the elements green, yellow, and blue because they have the same number of elements, or they have the same cardinality, which is equal to 3. If the set does not contain any element, it is called as an empty set or a void set or a null set. And it is denoted by this symbol, pair of braces, or the Greek letter phi. The statement P is an empty set is written in symbol as, so we read this one as P is an empty set, telling us that there is no element inside set C, and that its cardinality therefore is equal to 0. On the other hand, if a set contains exactly one element, we call it as a singleton set or a unit set. So in this example, set S is a unit set because there is this one element inside the set. Set T is also a unit set because it contains one element inside the set. So we end up our discussions in here. In the next video, I'm going to discuss more about sets. Thank you for watching.